In this video, we'll be having the introduction to exponential functions. Please do not expect that there will be the common or the general main definitions of what an exponential function is. You can find other videos about it. What makes this video quite unique in some way or quite specific is that we'll be focusing on the basic form, recalling a few lessons such as the properties of exponents, as well as analyzing a few exponential equations and their corresponding graphs. And yeah, know the other characteristics of what an exponential function is and what isn't an exponential function, including the Euler's number and yeah, many others. So let's start. We do have to compare and contrast the difference and similarities of polynomial functions and exponential functions. So you can already see here that for the basic forms of these two functions, for polynomial, we have a typical f of x is equal to x raised to 3, while for exponential, we have f of x is equal to 3 raised to x. Now, you may see a difference, but what is the same with the two is that we both have the typical f of x. We both have the equal signs, and for the term at the right side of the equation, the general equation, we can see that there's a difference in the values accounted for the base and the exponent. So, acknowledge that for the polynomial function formula, our base is always the variable, and our exponent will always be a constant. For polynomial functions, I suppose that this lesson has been introduced before learning exponential functions, because exponential functions is a higher lesson than a polynomial. Usually when you're in second year high school or in third year, or most probably in first year high school, introduction of elementary algebra, you'll be encountering polynomial functions or functions with lower exponents such as x raised to 2, the squares, those kinds of stuff. For exponential functions, you do have to acknowledge that this time we have a constant base and an exponent variable. So basically, the roles of the base and exponent are different when it comes to the polynomial and exponential functions. For polynomial, we have variable base and exponent constant. For exponential functions, we have exponent variable and constant base. Therefore, let's focus now on exponential functions. Hence, we acknowledge that fx is equal to n raised to x, such that n will always be greater than 0. Or in some cases, n can be less than 0. I'm sorry. N can be less than 1, but not less than 0. I suppose that makes sense. Maybe numbers like 0.1 to 0.9 or 1/2, those kinds of numbers, they're still considered, with those bases, the equation is still considered an exponential function. But one thing that separates from understanding that it's an exponential function is that when x is less than 0, then that's a different conversation. N that is less than 0, or a base that is less than 0, is not an exponential function anymore. So we'll be having that in a few minutes. So first, we do have to practice, make some practice examples for properties of exponents. Let's solve some. Didn't really place the English label for each of these laws, but I suppose you may find the complete lecture about the properties of exponents, or in other words, the laws of exponents, in the very first video of this channel. You can just filter. You know what to do. Okay, for this first law, for example, if we have 2 raised to 2 times 2 raised to 3, you can see that we have a raised to x times a raised to y. You have to acknowledge that we just copy the base and add the exponents. So 2 plus 3, which is in other words equal to 5. Then 2 raised to 5 is 32. That's the answer. Okay, 2 raised to 2 times 2 raised to negative 6. Well, we do have 2 raised to negative 4 as a result. Because we have a negative exponent, we have to reciprocate the entire value. So we get 1 over 2 raised to 4, then we get 1 over 16. That is our final answer. For the second law, we have one example, 2 raised to 3 raised to 2. I suppose that's how you dictate it. Please correct me if I'm wrong. Which is equal to 2 raised to 6, because 3 times 2 is 6. Whenever we have a typical a raised to x and there is an exponent at the outer part of the parenthesis, basically we just multiply x and y. So in this kind of fashion. With that, 2 raised to 6 is basically 64. That's our final answer. Okay, for AB, open close parenthesis AB raised to x is equivalent to a raised to x, b raised to x. So we have an example, 2 raised to 1 over 2 times 8 raised to 1 over 2. Okay, we place them together to the bases. They may be different in value, but just situate them together in this fashion. Then at the outside part of the parenthesis, we place 1 over 2, the exponent 1 over 2. So we have 16 raised to 1 over 2. There's a specific rule that when you have a fraction exponent, you copy the base, confine it within a radical sign, and you place the numerator as the exponent of the base inside the radical sign, and place the denominator of that fraction exponent outside the radical sign. So in this case, 16, get the square root of 16, which is 4. So yeah, this is the final answer. For a over b, open close parenthesis, a over b raised to x. We have an example, 2 over 3, both exponent is negative 3. Basically, again, whenever we have a negative exponent, we have to reciprocate. So we have 3 over 2, both raised to 3. We filter this way. But still, I don't think that step is necessary. We just have to see that 3 times 3 is 9, times 3 is 27, 2 times 2 is 4, times 2 is 8. So yeah, 27 over 8. Let's move to this part. 3 raised to 7 over 3 raised to 9 is equal to 3 raised to 7 minus 9, which is basically 3 raised to negative 2. Again, with a negative exponent, we reciprocate, and hence we get 1 over 9. So I won't be placing further examples for these. You can feel free to really find the first video of this channel. It's basically all about lots of exponents. It's not lectured in digitally. It's not lectured digitally. It's written in bond paper. So yeah, that's the only video where I used bond paper for lecturing. Okay, let's move on. We have to recall that the general form for the exponential function is this, or as n is greater, should always be greater than 0. So here are examples about n being the base, or n being greater than 0. So we can see here, for this example, we have 2. 2 is greater than 0. N should be equal to than 0. So let's substitute the values. Our typical algebraic manipulation, g of x is equal to 2, such that x is equal to 2 raised to 2. So gx is equal to 4. Such that is 4. Now, g of x is equal to 2, given that x is 1, so 2 raised to 1, we get 2. And if x is 0, so 2 raised to 0 is 1. I think, yeah. 0 exponent rule, the answer will always be 1. And for if x is equal to negative 1, then reciprocate, we get 1 over 2. If our exponent is negative 2, so yeah, we get 1 over 4. Right. So the reason why we're doing this, we're filling in the values, provided that we have a value of x. We need it to show something in the Desmos graph. So I did use Desmos for showing the graphs, and for this example, it corresponds to this graph, and we know that this equation, the end or the base is greater than 0. So if the exponential equation obeys the rule that n is greater than 0, then we get this kind of graph. For the next example, h of x, okay, let's substitute the values. H of x is equal to 3 raised to 2, which is 9. If x is 1, we get 3. If x is 0, negative exponent rule, we by default get 1. If x is negative 1, we get 1 over 3. We reciprocate. If x is negative 2, we get 1 over 3 raised to 2, which is 1 over 9. Right. Still, this example follows the general rule that the base is greater than 0, because the base is 3. 3 is greater than 0. Therefore, we have this graph. As you may have observed, both of these graphs have an intersection in the y-axis. It will always be 0, 1, unless, under normal circumstances. So yeah, let's proceed with the other supplementary definitions about exponential functions. So again, this is the formula, the general form. As long as n, or in other words the base, is greater than 1, the graph will always be increasing. So you may have observed that both of these examples, g of x and h of x, follow the formula, follow the general rule that n is always greater than 0. The graph is always increasing. So if you can see the graph that is increasing, you'll always see this kind of I'm not really sure if we call it a parabola. Please correct me if I'm wrong, but yeah, please understand that it's this kind of curve. The function never crosses the x-axis since there is no value to substitute or to assume for x that will yield an answer of 0. As you can see, these graphs never cross the x-axis, but they do cross or intersect the x-axis. And the x-axis is a left horizontal asymptote. Alright. In this graph, I basically included both the equations of g of x and h of x in one representation just to show the difference between um, if you have a larger base or a smaller base, as long as they're greater than 1, I think, or yeah, as long as they're greater than 0. A smaller base, for instance, g of x, we have a base of 2, the graph will rise more gradually, or uh, in my own language, I call it slowly, because the, the equation with the larger base will have its graph rise more quickly or faster, since the base is greater than the base of g of x. So I hope you can see a visual, something that's pretty obvious already. You can see that the graph that's marked in red represents the equation that's written in red ink, and the blue graph corresponds for the blue equation, the equation written in blue ink. So the larger the base, the more quickly the graph rises. The smaller the base, that is still greater than 0, the graph rises more gradually or slowly. Then, as I've said earlier, exponential functions will never or not have negative bases. So n will always be equal to 1. When n is less than 1, this is really wrong. This is not an exponential function anymore. So I'll introduce to you Euler's number. Euler's number. I used to pronounce this as Euler, but I realized that you pronounce it as Euler's number. Euler, as in, it's a German surname. Euler's number is proposed by the Swiss mathematician, uh, the Swiss mathematician Leonhard Euler, back centuries ago. So basically, the quantity for Euler's number is, please bear with me. I need a few seconds to, okay. Euler's number is equivalent to approximately 2.71828169. So yeah, this is it. In the study of exponential functions, you will be seeing Euler's number as a common site, and I'll be teaching you how to address or how to solve with these quantities, especially when you solve exponential equations or functions. Exponential functions with positive bases that are greater than 1, that are less than 1, have decreasing graphs. So as you can see here, I'll give you one example. J of x is equivalent to 1/2 raised to x. So 1/2 in decimal is 0.5, which is less than x. So considering that 0.5 is our base, it'll be having decreasing graphs. Decreasing graphs are seen as graphs written this way. Increasing graphs are written this way, as we've seen examples earlier. For decreasing graphs, they're written this way, in that fashion. So yeah, that's it for this video. Please await for some more lessons related to introduction to exponential functions, as well as for a new lesson called logarithmic functions. So yeah, thank you for watching.